Hello and welcome to this Accelera workshop on UVM-AMS, a UVM-based analog verification standard. In this workshop, we're going to give you an update from the Accelera UVM-AMS Working Group and share with you the direction the working group is taking in bringing the idea of a modular, reusable verification methodology to the analog and mixed signal world. Let's get started. I'm Tom Fitzpatrick, Strategic Verification Architect at Siemens EDA, and I'll be providing an overview of UVM-AMS and why we're embarking on this journey with and for you. After that, Shekar Chetput from Cadence will give an overview of what the UVM-AMS framework will look like, followed by Joen Westendorp of NXP, who will share some details on additional infrastructure to facilitate abstraction and communication. Then Xiang Li from Qualcomm will show you some module-based ideas to facilitate communication between the test bench and various AMS model types. And finally, Lakshmanan Balasubramanian of Texas Instruments will wrap things up for us, after which we'll do a Q&A. So the Wilson Research Group, commissioned by Mentor, which is now Siemens EDA, has done a biannual survey of the ASIC and FPGA communities for the past several years. One important factor that the survey has tracked is the type of flaws that have contributed to ASIC respins. Here you can see that analog issues are contributing significantly to the need for ASIC respins. As my friend Brian Bailey wrote in a recent article in Semiconductor Engineering, quote, "Many of the legacy methodologies where analog and digital were designed and verified separately are having to be rethought," unquote. So the UVM-AMS Working Group is rethinking things, as you'll see. This slide shows a chart from the research firm International Business Strategies, which says that 85% of design starts over the past 5 years have been mixed signal in nature. Such continued dominance of mixed signal, cutting across several industries, including 5G, automotive, IoT, and others, is leading to more recognition of the risks and challenges in mixed signal verification. Just like we did 10 years ago with UVM for digital verification, teams are now beginning to realize that AMS verification is going to require more advanced methodologies for modular, scalable, reusable, coverage-driven verification of mixed signal designs. Here you see a list of the companies that are currently participating in the UVM-AMS Working Group. Since the group is part of Accelera, you do need to be an Accelera member to participate in helping to develop UVM-AMS. If you're not currently in the working group and would like to be, we'd love to have you. You can find all the information you need at accelera.org. And if you're not an Accelera member and would like to participate, you can go there to become an Accelera member and then join us in the working group. So before we get too far into things, I'd like to take a moment here to make sure that we all agree on the terms we'll be using. Analog mixed signal simulation and verification refers to systems that can simulate and verify AMS designs either through co-simulation, where a digital engine is combined with an analog or electrical solver, or with an event-driven digital engine that can include analog real number models. This is sometimes referred to as digital mixed signal simulation, or DMS. And just so we're all talking about the same thing, UVM is the IEEE 1800.2 standard verification methodology originally released by Accelera 10 years ago that provides modular, scalable, reusable, and interoperable verification IP, stimulus, test bench components, environments, and more. This is in use by over 80% of ASIC verification teams today, so it makes sense that we'd use this as our target methodology. And when we combine these ideas, we get UVM-AMS, a comprehensive and unified analog mixed signal verification methodology based on UVM to improve AMS and DMS verification of integrated circuits and systems. But what exactly do we mean by that? Well, we're planning to define a set of class-based extensions to UVM, along with an accompanying set of components and/or packages in System Verilog or Verilog AMS, including stimulus, tests, sequences, components, and analysis functions, including monitors, coverage, and other analysis. The goal obviously is to improve verification for mixed signal designs, whether they are primarily analog or primarily digital. We will define a framework for the creation of reusable components and test benches for AMS verification by extending the concepts such as agents and sequences that are so successfully used in UVM today. Our work will be based on existing standards as much as we can, and if any extensions are deemed necessary to existing standards, UVM-AMS will define them as narrowly as possible to minimize dependencies on other standards work. And lastly, the UVM-AMS Working Group is committed to promoting the use of UVM-AMS throughout the verification community and you can consider this workshop today to be the first step along that path. So the first thing we did in the working group was to compile a list of requirements. Each member company provided their list of requirements, and then we consolidated the list to align the requirements and eliminate duplication. Then we voted on the requirements, with each company ranking each requirement, from which we created a prioritized list of requirements. And there are currently over 60 requirements on that list. The requirements can be broken down into an unsurprising set of categories, if you're familiar with UVM. We divided them into requirements related to drivers, sequences, monitors, coverage and assertions, data types, and finally, the category that all you analog folks will easily recognize, but might be a new concept to you UVM folks, is connect modules. We'll talk about those a little later in the presentation. Some other general requirements are to support transient analysis of analog signals, to facilitate verification when you have many different types of models, and most importantly, to extend concepts from digital verification, like assertions and coverage, to the analog and mixed signal domains. We certainly hope that UVM-AMS addresses the lack of a comprehensive methodology for AMS verification, and will bring to it many of the advantages that folks on the digital side have been enjoying for a decade with UVM.
Hi, I'm Shekar Chetput from Cadence. I'm going to be walking you through the UVM-AMS framework section of this workshop. First, let's rewind back to sometime in 2014. At this time, mixed signal verification was typically performed using traditional module-based verification approaches. We could refer to this approach broadly as the pre-UVM mixed signal verification. In such an approach, both the design and the test bench was defined via modules. The stimulus for the test bench was also often generated via modules, while out-of-module references, also known as OOMRs, were used in the test bench to either drive stimulus into the design or monitor results. Quite often than not, all test case information was also provided in a single file. In DVCon 2014 Europe, there was a presentation from Freescale called UVM Ready, transitioning mixed signal verification environments to universal verification methodology. This presentation took a step forward by defining an approach to apply UVM-based concepts on the test bench created for mixed signal verification. In the process, it demonstrated how such a verification framework could be reusable and took a step towards more comprehensive digital-centric mixed signal verification. Simply put, it opened the door for exploring UVM-ready mixed signal verification in our industry. About a year later, in DVCon 2015, there was another paper, this time by Cadence, on the how-tos of advanced mixed signal verification. This paper did a deeper dive on creating reusable mixed signal verification frameworks that are not only UVM ready, but also more metric driven. It introduced a mixed signal UVM verification component called DMS wire, along with a methodology that deploys a gasket to enable reconfigurable designs with various abstractions, be it logic, real number models in Verilog AMS, or electrical, including spice blocks. This approach opened even more exploration towards UVM-based mixed signal verification, where digital verification concepts like assertions, coverage, and metric-driven verification can be deployed on mixed signal designs. Fast forward over the next 5 years, we saw many customers across the industry deploy and explore these basics concepts. During this time, our industry was also increasingly deploying more system Verilog based design and verification approaches. including behavioral modeling using system Verilog RNN, assertions, SV and SPICE, co-simulation, and so on. With the increasing awareness and needs here, as well as a lot of learning and customization that was happening in the industry in this area, it was about time to create a standard around UVM-AMS that would further elevate the mixed signal verification process and open the doors for reusable mixed signal verification IP as well. Before we look at the high-level framework for UVM-AMS, let's look at a couple of key requirements regarding data types that are essential for this framework to deliver on its goals. The first one is regarding the support for randomization of real numbers, which are needed for more efficient metric-driven mixed signal verification. The next one is the ability to express and process complex numbers, spectra, and transfer functions. The third one is regarding the verification IP, which needs to have the ability to interface with the design module across multiple abstractions without the need for inserting connect modules. This will allow the UVM-AMS framework to be able to maximize the ability to expand on the baseline UVM layer, while also allowing the ability to freely switch abstractions between electrical or WReal or SV RNM at the design layer. With those high-level requirements in mind, let's look at the high-level framework for UVM-AMS next. Before we look at the mixed signal components of the UVM-AMS framework, let's first understand the three key components of a digital UVM environment. The first key component is called a digital agent, which has three elements: a driver, a sequencer, and a monitor. The driver element drives the DUT. Next, think of the sequencer as an advanced stimulus generator that controls the items provided to the driver for execution. Finally, the monitor samples DUT signals to collect information and perform various checking and coverage. By separating the concept of driving the data from the concept of generating stimulus and the concept of monitoring results, the digital agent provides the ability for those elements to be created and working independently of each other. Such a structure leads to improved reuse and quality of those elements in a verification environment. The UVM environment class is the top level component of the UVM verification component. This environment class is designed to provide a flexible, reusable, and extensible verification component. In this environment, agents can be configured, stimulus could be managed via virtual sequences, and the results could be processed via scoreboarding to determine overall coverage of the verification plan. With this baseline understanding of how UVM works, let's look at the UVM-AMS framework extensions next. In the UVM-AMS framework, we introduce the concept of an analog agent, which will be used to manage similar requirements on the analog mixed signal aspects of verification. This analog agent will interface with the mixed signal DUT either via standard interfaces in System Verilog or System Verilog APIs, which would in turn leverage what we call as analog resources to either drive various abstractions of the signal in the mixed signal DUT or sample those abstractions as needed and deliver those samples back to the monitor in the UVM-AMS layer. In short, imagine the analog agent role to be managing a discretized version of the analog signals in the DUT. With such an approach, the UVM-AMS framework is able to seamlessly expand on the baseline UVM capabilities while relying on standardized system Verilog-based access mechanisms to integrate with the various abstractions of digital or analog mixed signal designs, thereby achieving comprehensive, reusable, and metric-driven mixed signal verification. In the next few slides, we will double-click on the requirements for the specific elements of the analog agent and then touch on the requirements for the core digital mixed signal concepts like coverage and assertions, which are needed to achieve metric-driven verification with UVM-AMS. In this slide, we focus on the driver element of the analog agent and its interaction with its sequencer, which are essentially the left-hand side of the picture shown here. The driver will work with the module-based analog resources in the physical layer, which might be implemented in either the discrete real number modeling world or in the continuous domain electrical world. The driver should be issued a command by the sequencer and execute it without blocking the flow of execution that requested the change. The driver shall deliver variables to the analog resources where the physical aspects of the drive, either discrete or continuous, are actually implemented. The driver may notify the sequencer when the individual variables of the command have reached their final values. The driver should support waveform generation that is independent of the actual nature being driven. For example, a voltage or a current. The driver should support more sophisticated output as well, like tri-state sources with impedances and so on. Next, we'll look at a couple of sequencer requirements. The sequencer shall issue sequence items to the driver. The driver may notify the sequencer when the individual variables of the command have reached their final values. Next, we'll look at a couple of requirements on the monitor and how it interacts with the analog resources in the module layer. The picture in the middle of the slide tries to zoom in to the right side of the analog agent, which is the monitor, and it tries to show the interaction between the monitor and the duct, which is the top level harness here, through the block called analog resources. The analog resources shall sample physical aspects of a signal, either discrete real number model or continuous electrical signals, and deliver these samples to the monitor. The analog resources need to, of course, understand when to take the samples. The sample may be instantaneous or defined over a period of time. The analog resources may sample analog expressions as well. This slide summarizes the requirements on two more key technologies of UVM-AMS framework, being the coverage and the assertions. UVM-AMS shall support assertions to check measurement correctness. UVM-AMS shall support assumptions to check the validity of input data, including signaling error conditions in drivers. And assumptions shall support the same domains as assertions do. Special constructions shall be provided to specify assertions, assumptions, and coverage checks, and they may be functions, classes, or class methods. The need for extensions to existing language features like assertions and coverage are discussed in more detail in a couple of papers that are presented by experts from IIT Kharagpur and Texas Instruments. For more details, you can refer to those papers. Monitors it shall convert actual simulation data into abstract data types used by checkers. Analysis of signal scopes, performing modulation and demodulation, checking of a signal period, a duty cycle, etc. will also be possible. Thank you.
My name is Joen Westendorp. I'm working with NXP semiconductors. Today I will walk you through the slides discussing the capabilities and extensions of UVM for AMS, which will lead to higher verification efficiency in the AMS verification domain. The first and most important capability of UVM for AMS is the support for verification of the physical layer. The UVM standard itself does not enable AMS verification. AMS verification has further requirements for the coordination of stimulating and measuring a signal with respect to digital verification. For example, an analog signal can have any wave shape. This wave shape needs to be specified. Also, the start of a measurement needs to be triggered. The extensions to UVM defined by the UVM-AMS Working Group will close that gap. The main goal of the standard is to apply UVM methods and techniques to AMS circuits and systems. The second capability of UVM-AMS is to drive and monitor all types of signal abstractions. A test bench structure will be defined, which extends the use of UVM components and the extensions thereof into the physical layer, enabling AMS verification. This means that a driver or a monitor extends into the physical layer and is able to generate or sample analog signals. The defined solution will not depend on the abstraction level of the AMS signals. An analog signal can be electrical, it can be real valued, it can be Verilog AMS, it can be a system Verilog user-defined net type, and so on. But this does not affect the defined solution. And the standard will aim to eliminate the need to rely on conversion elements to change the abstraction level of the AMS signal. This means that the test bench component will interface with the DUT at the same abstraction level, whether it be electrical, real valued, or some kind of user-defined net type. The third and last capability which UVM-AMS offers is the separation of tests and test benches. As in UVM, stimuli for AMS verification will be independent of the test bench and the design. This way, the test and the test bench can be independently reused, leading to higher verification efficiency. As much as possible, UVM-AMS will adhere to the sequence item mechanism used by UVM. But if necessary, UVM-AMS will define extensions to these UVM-based classes to define AMS-specific stimuli. Examples which came to mind are, for example, the timing of signals, which is not supported by the standard UVM sequence item mechanism.
Hello everyone, my name is Xiang Li. I am from Qualcomm. In this session, we will summarize considerations about module-based facilitation to interconnect UVM-AMS class-based environment and the analog design under test. This slide is about analog resources. As shown in one of earlier slides, Verilog AMS provides connect modules to connect between abstractions of interconnected signals. The UVM-AMS framework does not define any need for insertion of connect modules. Analog resources will encapsulate abstractions that could be simulated either in digital solver as a real number model or analog solver as electrical space signals. This picture shows an example of the test bench based on UVM-AMS framework discussed earlier. Let us assume there is an USB 3 file with 4 analog pads. If the design is provided as space netlist, the signals will be in the form of voltage control the voltage source or current control the current source, etc. Inside the analog resource module, a type of adapters will be provided to enable UVM-AMS drivers and monitors to interface with the different kinds of models of analog design. In this example, the model of analog design is a space netlist. The adapter will present the signals and the interconnections to meet the requirement for simulation with analog solver in this case. The standardization of the adapter is under discussion. Before the standardization, reference design examples will be provided to cover majority of typical use cases. In this example, the adapter is to drive monitor voltage current source ports. In the second example, the design model will be Verilog AMS model. Then the signals will be electrical voltage or electrical current. The adapter will present the signals and the related interconnections for UVM-AMS drivers and monitors to interface with the Verilog AMS model in order to meet the requirement of analog simulators. In this example, the adapter is to drive monitor electrical ports. In the third example, design model is a real number model. Then the signals will be real ports. The adapter will present the signals and the related interconnections for UVM-AMS drivers and monitors to interface with real number model in order to meet the requirement of either a digital solver or an analog solver. In this example, the adapter is to drive monitor real ports. So far, we have discussed about the 3 simplified examples. For more complicated cases, further study is needed in order to make proposal for standardization.
Hello, we had Tom from Siemens introducing us to the UVM-AMS workshop, Shekar from Cadence providing a high-level overview of the UVM-AMS framework, followed by Joen from NXP explaining the additional infrastructural requirements, and Xiang from Qualcomm provided us the additional presentation needs required to enable the module-based contents work seamlessly with proposed UVM-AMS framework. Here I am, Lakshmanan from Texas Instruments India Private Limited. I would like to wrap up this workshop with a set of 3 frequently asked questions that one would have after going through this workshop, and our answers to that, followed by concluding remarks. The first question could be, what value will the UVM-AMS standard bring to the technical community? Our answer is, the UVM-AMS Working Group envisions the availability of an industry-agreed analog and mixed signal verification methodology based on its planned UVM-AMS standard. This will encourage support by the tool and IP providers offering ready-to-use analog and mixed signal verification IP that can be integrated easily into a UVM-AMS test bench. It will raise the productivity and, of course, the quality of analog and mixed signal verification across projects and applications, thanks to the reuse of proven verification components and stimuli. The next one is, I currently use interface verification IP, which only supports digital signals. Should I replace them with AMS verification IP? Our answer is no, but just augment it. The objective of the UVM-AMS standard is to introduce dedicated capabilities that enable making AMS extensions to digital-centric verification IP. As UVM offers the foundation technology, we could benefit from using test bench configuration, factory-based component overrides, and virtual interfaces to seamlessly insert AMS components, signals, and analysis in an existing digital-centric verification IP. Obviously, this extension heavily depends on the flexibility and configurability offered in the underlying digital VIP itself. Finally, I quote, will the UVM-AMS Working Group develop specific AMS verification IP? Our answer is, the primary objective of the UVM-AMS Working Group is to develop a standard that forms the framework to develop AMS verification components and test benches. As such, the working group itself will not develop these elements. The internal functionality to drive, monitor, or analyze AMS signals should be developed by the verification team, probably with their EDA vendor partners. However, to explain how to create an AMS verification IP or test benches to the AMS verification community, it is expected that there will be basic examples available as part of the deployment of the UVM-AMS standard. To conclude, we have seen through this UVM-AMS workshop a very necessary and definite need for more advanced standard methodologies for scalable, reusable, and metric-driven mixed signal verification. Towards that, the UVM-AMS standard proposes and plans to address the gaps in the current verification methodology standards by targeting analog and mixed signal contents, application and extension of existing UVM concepts and components like driver, sequencer, monitor, connect modules, coverage and assertions, and data types. And finally, extend the UVM class-based approach to seamlessly support the handling of module-based mixed signal contents with appropriate adapters and verification methods. we have given a glimpse of what the UVM-AMS standard will look like, and we would like to invite you all to be part of the development and contribute to it constructively. These are some of the references that we have used in our presentation, the past work that we have extensively quoted. Thank you very much for your kind attention and interest in this workshop. Thank you.
Thanks for wrapping it up so nicely for us, Lakshmanan. So now we'd like to open up to general Q&A. Thanks.